Now let's see an example with multiple constraints. We want to find the maximum of the function f of xyz equals x subject to two constraints. 2x squared plus 7y squared plus 5z squared is equal to 3, and x plus y plus c is equal to 0. So there's a single objective function, but there's two constraints that have to be satisfied. What's a picture here? A picture here is that okay, if it was just x squared plus y squared plus z squared equals something, that would be a sphere. But the x, the y, and the z each separately got rescaled by different amounts. So it's a sphere that's been compressed and stretched in different directions. So this is a surface called an ellipsoid. And it's basically a squashed sphere. So, well, here's a sort of simplistic drawing of an ellipsoid. Something like that. And then x plus y plus z equals 0 is a plane with normal vector 1, 1, 1, right? It's a plane that sort of cuts across this ellipsoid. So let's see, we can draw it like this. It cuts in front of the ellipsoid and then comes up behind it like this. And what we're interested in is the intersection where the plane goes through the ellipsoid. So imagine that this ellipsoid is a loaf of bread, and we sliced across it with a slicer, and the circle is the edge of the cut. It's not drawn very well, but that's the idea. It's the edge of the cut. So on this curve, we want to maximize the value of x. So we want to move as far as possible in the x direction on this curve here. Okay, so the idea is that instead of having parallel gradient vectors, the gradient vector of the objective, instead of just being parallel to the gradient of one constraint or the gradient of the other constraint, so it's not just a scalar multiple of the first one, and it's not just a scalar multiple of the second one. Instead, what it is those added together. And now, do you remember in our first chapter, chapter 12, where we actually talked about having a vector times a scalar plus another vector times a scalar? That was a linear combination. Was the term there. So the gradient of the objective is a linear combination of the gradients of constraints. So that's the idea behind the approach for a multiple constraint problem. So let's at least take the first step, couple steps in the process of solving this one. So our function was f equals x, and the gradient of f is 1, 0, 0. Our first constraint was 2x squared plus 7y squared plus 5z squared, or that's the constraint function anyway. Then the gradient is, do you know? 4x, 14y, 10z. And our last constraint function was x plus y plus c, and the gradient there is 1, 1, 1. So we have the vector equation that gradient of f is a scalar times gradient g plus a scalar times gradient h. If you expand that out, you get the equations. 1 is lambda times 4x plus mu times 1. 0 is lambda times 14y plus mu times 1. And 0 is the last 0 in f is lambda times 10z plus mu times 1. So here are the entries of f, 1, 0, 0. And the entries of g and the entries of h are 1, 1, 1. And that just comes from writing out these vectors and setting the x's, the y's, and the z's to be equal. And then we also have to have the constraint equations. And this time there's two constraint equations. 2x squared plus 7y squared plus 5z squared equals, what was it? 3. It equals 3. And then x plus y plus z, I believe this one was set to be 0. So that's our system of equations. It has 5 equations. It has 5 unknowns. X, y, z, lambda, and mu. So to the extent that we want to set up the system of equations, there it is. And now the solution is, it's just a bunch of algebra, but maybe I won't go through it. The solution takes some steps, but you end up with 2 critical points, x, y, z could be either minus 6 over square root 59, 5 over 2 times square root 59. So I'm copying this down from my solution that I have written down here. And 7 over 2 times square root 59. That's a critical point. And then the opposite of that, the minus 1 times it, is also a critical point. So it could be plus or minus that. And the values are f of x, y, z is x, and we end up with plus or minus 6 over square root 59 as the two values. So plus is the maximum and minus would be the minimum. Okay, so I invite you to try going through this solution for yourself if you like, but maybe, the thing that I really need you to do is make sure you understand how we figured out those gradients and how we set up those that system of equations. I hope that part made sense for you.